Pick up anything near you. A glass, a coin, your phone. Feel the weight of it, the hardness, the way light moves across its surface. You trust these things because you understand them. Glass is transparent. Steel is strong. Rubber bends. Every material you've ever touched obeys a set of rules written into the atoms themselves. Chemistry dictates what a substance can and cannot do. Always has. Since the first human shaped a stone into a blade, we've been working within nature's inventory, finding materials, testing them, learning their limits. But what if the rules were optional?
What if you could build a material that bends light the wrong way? Not a little bit, not approximately, but in the exact opposite direction that every lens, every window, every prism in the history of optics has ever bent it. A material that gets thicker when you stretch it, as if tension and compression have switched places. A material that can reprogram its own properties, on command, in real time, like software updating itself inside a solid object. These are not thought experiments. They exist. They're called metamaterials, and they represent something unprecedented in the history of human engineering. For the first time, the properties of a material are determined not by what it's made of, but by how it's shaped. Geometry has beaten chemistry, and what that unlocks is barely short of magic. This is the story of how we learned to build the impossible. It begins, as many great stories in physics do, with a paper that nobody read. In 1967, a Soviet physicist named Victor Veselago sat at his desk at the Moscow Institute of Physics and Technology and asked a deceptively simple question. What would happen if both the electric permittivity and the magnetic permeability of a material were negative? These are two fundamental properties that govern how electromagnetic waves, light, radio, microwaves, interact with matter. In every known substance, at least one of them is positive. Veselago wanted to know what the mathematics predicted if both went negative simultaneously. The answer was extraordinary. Light would refract in the opposite direction. Not slightly, not approximately, backward. Where a beam entering glass bends toward the normal line, predictably, reliably, as Newton himself described, a beam entering Veselago's hypothetical material would bend to the same side as the incoming ray. Lenses could be flat slabs. The Doppler effect would reverse. An approaching ambulance would sound like it was retreating. Phenomena that physicists had taken for granted for 3 centuries would flip on their heads. He published his findings in Russian in 1967, and an English translation appeared the following year. And then, silence. For 33 years, nothing happened. The paper was cited occasionally, read rarely, applied never. Not because the physics was wrong, the mathematics were impeccable, but because no natural material has ever exhibited both negative permittivity and negative permeability at once. Veselago had written an elegant recipe for a dish with ingredients that didn't exist anywhere in the known universe. He would wait more than 3 decades for someone to prove him right. He died in 2018, at the age of 89, having lived to see his forgotten paper become one of the most cited works in modern physics. But ingredients, it turns out, can be invented. In the late 1990s, Sir John Pendry at Imperial College London had a quiet revelation. He realized you didn't need to find atoms that behave this way. You could build structures that behave this way. Tiny copper split-ring resonators, smaller than a wavelength of light, arranged in precise geometric patterns on a circuit board.
Each ring on its own is unremarkable, ordinary copper, ordinary geometry. But together, arranged with mathematical precision, they trick electromagnetic waves into responding as if they've entered an entirely new kind of substance. In the year 2000, David Smith and his team at the University of California, San Diego created the world's first metamaterial and demonstrated negative refraction. Light entering this material bent in the opposite direction from everything physics had ever observed in nature. When Smith's team went digging through the literature, they stumbled upon Veselago's forgotten paper. A prediction made 33 years earlier, gathering dust in a Soviet journal, had just been proven correct. The scientific community was electrified. Some were skeptical. The basic concepts taught in introductory physics courses suddenly needed rethinking. As Smith later reflected, nearly everything about how waves behave in these materials challenged deeply held intuition. The learning curve was steep for the entire field. But the real shock was still coming. In May of 2006, John Pendry, David Schurig, and David Smith published a theoretical paper in Science that read like science fiction. They proposed that a metamaterial could be designed to guide electromagnetic waves around an object, the way river water flows around a smooth stone, so that the waves emerge on the other side as if the object were never there. An invisibility cloak. The math was rigorous. The concept was called transformation optics. By carefully varying the material properties from point to point through a metamaterial shell, you could warp the path of electromagnetic waves with the same precision that general relativity warps the path of light around a star. Except here, the warping was intentional, engineered, controllable. Pendry later said the idea started partly as a joke, but the equations held, and when Smith saw them, he knew instantly. They had to build it. 5 months later, in October 2006, Smith's group at Duke University unveiled the result: a metamaterial cloak, designed to operate at microwave frequencies around 8.5 gigahertz, constructed from concentric rings of copper split-ring resonators, each ring carefully tuned, its dimensions subtly varied from the last to create a precise gradient of electromagnetic properties across the structure. Inside the cloak, a copper cylinder. They aimed a microwave beam at the assembly, placed the whole apparatus between two metal plates in a test chamber, and measured the fields with a specialized detector. The wave fronts separated, flowed around the cloaked region, and recombined on the other side, their phase largely intact. The copper cylinder cast no meaningful shadow. To the microwaves, it had effectively vanished. Now, let's be honest about what this was and wasn't. The cloak worked for a narrow band of microwave frequencies. It was two-dimensional. It was not invisible to your eyes. Smith himself noted that the cloak actually scattered more energy than the bare cylinder at frequencies away from the design target. A full-spectrum, visible light invisibility cloak remains, as of today, a problem for future generations. But the principle had been proven, and that mattered enormously. Because the same design framework, transformation optics implemented through metamaterials, didn't just apply to cloaking. It applied to any manipulation of electromagnetic waves, lenses that beat the diffraction limit, antennas smaller than should be physically possible, devices that concentrate, redirect, and sculpt energy in ways no natural material permits. Science magazine named it one of the top 10 breakthroughs of the year, and metamaterials went from a curiosity to a discipline. But here's the thing about a good idea. Once you understand that the structure of a material can override the nature of its components,
the implications ripple outward, far beyond light, far beyond cloaking. Because electromagnetic waves are not the only waves we can manipulate. Sound obeys similar equations. Mechanical force follows its own rules. And in every domain, the same radical question applies. What happens when geometry overrides chemistry? The answer, it turns out, is that the impossible keeps showing up. Here's something worth pausing on. Stretch a rubber band. Watch it from the side. It gets thinner in the middle. That's what every familiar material does. Pull it longer, it gets narrower. This is governed by a number called the Poisson's ratio, and for virtually every substance you've ever handled, that number is positive. Now imagine pulling a material and watching it get wider, thicker, as if the material is pushing outward in defiance of common sense. Materials that do this are called Auxetics, and their Poisson's ratio is negative. How? Geometry. The internal structure, often a lattice of reentrant shapes, like tiny bow ties or rotating polygons, unfolds when tension is applied. The architecture of the cells causes them to expand perpendicular to the pull. Same atoms, same chemistry, but the pattern they're arranged in reverses a behavior we thought was universal. Auxetics are already finding their way into body armor, where they densify at the point of impact, concentrating protection exactly where it's needed. The harder you hit an auxetic material, the denser and tougher it becomes at the strike point. Into medical stents, where they expand uniformly in all directions, conforming to the complex geometry of blood vessels in ways conventional materials never could. Into shoe soles that become more cushioned under pressure rather than less. Into tactile sensors for robotic hands, where the auxetic contraction under pressure amplifies the signal, making artificial fingers more sensitive than would otherwise be possible. And the field is accelerating. In 2024, researchers achieved a seamless auxetic substrate with a Poisson's ratio of -1, the theoretical limit for isotropic materials. That number means the material expands laterally by exactly the same proportion it's stretched longitudinally. Perfect symmetry. Perfect defiance. A material that does the opposite of what you expect, doing it better than anything nature provides. Because someone had the insight to ask, what if the shape matters more than the substance? For decades, the knock against metamaterials was permanence. Build a structure, fix its properties, and those properties are locked in forever. Useful, yes, but limited. Nature's materials adapt. Bone strengthens under load, skin heals, octopus muscle stiffens and softens at will. Metamaterials were frozen in place. Until 2024. At South Korea's Ulsan National Institute of Science and Technology, Professor Ji-Yun Kim's team unveiled something genuinely new: a digital mechanical metamaterial. Inspired by the octopus, an animal that can shift the stiffness, shape, and texture of its body in moments, they created a material whose mechanical properties can be reprogrammed in real time. The system works through what the team calls graphical stiffness patterns. Individual cells within the material can be switched between rigid and soft states, like pixels on a screen flipping between black and white. By encoding different patterns of stiff and soft cells, the material changes its shape, its flexibility, its response to force, all without swapping any hardware. The demonstrations was striking. An adaptive shock absorber that reconfigures itself upon impact, minimizing the force transmitted to whatever it's protecting. A force transmission material that selectively activates adjacent switches by routing pressure along chosen pathways. All controlled by digital commands. The first author on the paper, Jun Kyu Cho, put it plainly:
They had built a metamaterial that implements desired characteristics within minutes, without additional hardware. Professor Ji-Yoon Kim went further. This metamaterial, he said, is capable of converting digital information into physical information in real time. It will pave the way for materials that learn and adapt to their surroundings. Think about what that means. A material that doesn't just have properties, it receives instructions about which properties to display. A solid object that updates like software. The boundary between the digital world and the physical world, blurring inside a lattice of switchable cells. And almost simultaneously, at MIT, Carlos Portella's lab was solving a different piece of the puzzle. His team developed a framework for micro-scale acoustic metamaterials, tiny lattice structures with precisely positioned spheres that control how ultrasound waves travel through them. By adjusting the placement of these microscopic masses, they could tune wave velocities, guide ultrasound along specific paths, even split a single acoustic signal into multiple outputs. All at the micro scale. All published in Science Advances. This is the frontier. Materials that don't just possess unusual properties, but choose them. Materials that compute. Materials that respond. The line between a material and the machine is beginning to dissolve. And then there is the application that could save the most lives. Every year, earthquakes kill thousands of people, not through the motion of the earth itself, but through the collapse of what we've built on top of it. Buildings, bridges, power plants, structures that were never designed to dance. Seismic metamaterials propose a radical alternative to conventional earthquake engineering. Instead of making buildings more flexible or mounting them on shock absorbers, what if you could prevent the seismic energy from reaching the building in the first place? The concept mirrors electromagnetic cloaking, applied to the ground beneath our feet. Arrays of resonators, boreholes, underground pillars, carefully spaced columns, arranged at the scale of seismic wavelengths. When earthquake waves encounter this metamaterial barrier, they're redirected, steered around the protected zone. The waves keep traveling, but they go around the building, like the microwave cloaking experiment at Duke, scaled up to a city block. Researchers at the University of Missouri have demonstrated that pillar-type resonators can steer Rayleigh waves, the destructive surface waves that cause buildings to sway and collapse, along programmed paths. The EU-funded INSPIRE project tested metamaterial barriers using everything from borehole arrays to engineered gravel. In France, researchers even discovered that a forest of trees, if tall enough and spaced at the right intervals, functions as a natural seismic metamaterial. Their collective resonance disrupts surface waves. Though trees tall enough to dampen earthquake frequencies would need to reach nearly 100 meters, the principle proved sound. We're not there yet. Full-scale seismic cloaking for real buildings remains an engineering challenge, not a deployed solution. But the physics works, and the same idea extends to protecting infrastructure from train vibrations, industrial tremors, even the low-frequency hum of urban life. Imagine a hospital, or a data center, or a school wrapped in an invisible shield, not of metal or concrete, but of geometry. Patterns in the ground that whisper to seismic waves, "Go around." Not louder foundations, not thicker walls, just smarter shapes, placed beneath our feet, doing quietly what brute strength never could. Every material humans have ever used was a discovery. We found copper in the earth. We stumbled upon rubber in a tree. We melted sand and were astonished to find glass. For all of human history, we have been nature's students. learning what the periodic table allows, working within the constraints of chemistry, grateful for whatever properties the atoms happened to offer. Metamaterials break that pattern. For the first time, we are not asking nature what it can give us. We are telling matter what to become. Not through new elements or exotic compounds, but through architecture, through shape, through the quiet, revolutionary idea that how you arrange something matters more than what it's made of.
A copper ring on a circuit board, a lattice of tiny spheres, a grid of reentrant cells, ordinary materials assembled with extraordinary intention. And from that intention, light that bends backward, sound that travels where we tell it, solids that thicken when pulled, objects that vanish from the view of electromagnetic waves, earth that guides its own tremors away from the places where people live. We are not just engineering new materials, we are engineering new physics, new relationships with the forces that govern the visible world. And the truly humbling part is that we are still in the earliest chapters. The metamaterials of 2025 will look as primitive to the engineers of 2075 as Veselago's forgotten paper once looked to us. But it won't be forgotten again. This is Cosmic Canvas, where we turn the universe into a living gallery.
Until next time, remember that the most powerful material in the universe might not be found in the heart of a star. It might be found in the shape of an idea.